Organic chemistry lessons. In this module, we will be once again dealing with ammonia. In the previous module, we discussed only the nomenclature and some of the physical properties of amines. In this module, we will be dealing with the preparations of amines. These amines can be prepared in three ways. One is by the nucleophilic substitution using nitrogen containing nucleophiles. The other one is a reduction of nitrogen containing functional groups. The third one is a reductive amination of aldehydes and ketones. Apart from these three, we will come across a few more reactions based on rearrangements, with which also we can prepare amines. Nucleophilic substitution routes to amines. There are two ways by which amines can be prepared using the nucleophilic substitution reactions. One is the direct nucleophilic substitution. The other one is Gabriel synthesis, which is meant for the synthesis of primary amines alone. In the direct nucleophilic substitution reactions, a nitrogen containing nucleophile, usually ammonia, is treated with an alkyl halide. The SN2 reaction takes place here. Ammonia behaves as nucleophile and it attacks the carbon which is connected to the leaving group, usually the halide. Now after the SN2 reaction, we end with an ammonium halide. And this ammonium halide gets deprotonated with another molecule of ammonia, and we end with a primary amine. So here ammonia plays two roles. In the first step, this reaction involves two stages. In the first stage, ammonia behaves as nucleophile, and in the second stage, it behaves as a base. The reaction does not stop here. The primary amine once again behaves as nucleophile. Of course, it's still better nucleophile than ammonia. It attacks another molecule of alkyl halide, and we end with an ammonium salt, and after deprotonation we end with a secondary amine. And this secondary amine can once again react with another amine, alkyl halide, to give a tertiary amine, and this tertiary amine can react once again with another alkyl halide to give a quaternary ammonium salt. So in all these four reactions we have seen, the first stage is an SN2 reaction, which is favorable only with primary alkyl substrates. So always it's better to make use of methyl halide or any other primary alkyl halide in this reaction for preparing amines. And usually this reaction ends with a mixture of primary, secondary and tertiary amines, and hence this reaction becomes a reaction of less usefulness. We can end with only primary amine by using excess of ammonia, and for which I have given two examples here. N-propyl bromide on treatment with the excess of ammonia, we end with a primary amine. And here a primary alkyl halide is treated with a tertiary amine, and we end with a quaternary ammonium salt. So what we can understand from here is ammonia or amine we have to use in excess quantity so that we will end with only one product. Another nucleophilic substitution reaction by which we can prepare amine is Gabriel phthalimide synthesis. Here potassium phthalimide is behaving as nucleophile, nitrogen with negative charge. This behaves as nucleophile. This is treated with an alkyl halide. After a nucleophilic substitution, we end with N-alkyl phthalimide. This N-alkyl phthalimide, after hydrolysis, we end with primary amine. And this is the mechanism for the Gabriel phthalimide synthesis. We start with potassium phthalimide and alkyl halide. We end with N-alkyl phthalimide, which on hydrolysis we end with a primary amine. So this reaction is meant for the preparation of primary amines only. So in the previous method we have seen we are ending with mixture of products, whereas here we will end with only one primary amine. And here is another example for Gabriel phthalimide synthesis, and you can see a primary alkyl halide is treated with potassium phthalimide. After a SN2 reaction you get N-ethyl phthalimide, which on base catalyzed hydrolysis we end with ethylamine, and the overall reaction is the replacement of one nucleophile by another nucleophile. Bromide is replaced by an amino group. Another important method for the preparation of amines is the reduction of organic molecules with nitrogen containing functional groups. Nitro compounds, organic molecules with the nitro group, can be reduced with hydrogen and metal, like hydrogen, palladium, carbon, or metal with the acid. Here are some examples given here. This is an organic molecule with the nitro group. This is reduced to amine. So hydrogen with metal catalyst or metal with the acid can reduce nitro group into amine. And in another case, we are reducing the nitrogen containing functional group cyanide into amine. So in this particular example, we are deriving a nitrile from an alkyl halide, methyl bromide. So methyl bromide on treatment with sodium cyanide ends with acetonitrile or methyl cyanide. This cyanide molecules, organic cyanides or organic nitriles, on reduction with lithium aluminum hydride followed by hydrolysis, we end with primary amine. The amides can be reduced with the lithium aluminum hydride followed by hydrolysis to give a primary amine, secondary amine, tertiary amine based on the type of amide we use. When we use primary amide for reduction with the lithium aluminum hydride, we end with primary amine. Likewise, we prepare secondary and tertiary amines from amides. The next method is reductive amination of aldehydes and ketones. Here, a carbonyl compound ketone, if R or R dash is one among the two is hydrogen, then it is aldehyde. If both are alkyl groups, then it is ketone. An aldehyde or ketone on treatment with ammonia, we end with imine. This imine with reduction, after reduction with some hydride donors, we end with primary amine. And this is called reductive amination. For reductive amination, it's not necessary that we have to use always ammonia. We can use primary amine or secondary amine also. With an aldehyde or ketone, when you add a primary amine, you will end with an imine, which on reduction with sodium cyanoborohydride, we end with a secondary amine. Whereas the aldehyde or ketone on treatment with a secondary amine, we get an iminium ion, which on reduction the same sodium cyanoborohydride, we end with the tertiary amine. Usually, for these reductive amination reactions, we prefer to use sodium cyanoborohydride, which is derived from sodium borohydride by replacing a hydride by cyanide. And here is an example. Two examples are given here for reductive amination of the carbonyls. And there are some rearrangement reactions like Hoffman rearrangement, Lawson rearrangement, Smith rearrangement, Curtius rearrangement. In all these rearrangement reactions, the intermediate molecule obtained is isocyanate, alkyl or aryl isocyanate, which on hydrolysis we end with carbamic acid, which on heating will give an amine. Hoffman rearrangement. Here, a primary amide is treated with bromine and a hydroxide base. The detailed mechanism is given here. It is self-explanatory with all the arrow marks shown. So the primary amide on treatment with bromine and sodium hydroxide, it results in the formation of alkyl isocyanate. And here we have the alkyl isocyanate, which on base catalyzed hydrolysis we end with carbamic acid, which is thermally unstable, and this on heating we will end with primary amine after decarboxylation. The next important reaction is Lawson rearrangement, and here we are using an activated hydroxamate. Hydroxamic acid will have an amide with a OH group connected to NH, nitrogen, and here that OH has been acylated, and this is what we call as activated hydroxamate. This on treatment with the hydroxide base, we end with an alkyl isocyanate, and as we have seen in the previous case, on hydrolysis, we will end with carbamic acid, and the remaining procedure is the same as for Hoffman degradation. This is Curtius rearrangement. This is also meant for the preparation of amines, where the starting compound is acyl azide. This on heating we end with the alkyl isocyanate, which on hydrolysis gives carbamic acid as usual. After decarboxylation it gives primary amine. The detailed mechanism of preparing acyl azide from acyl chloride is given here. From acyl azide we end with alkyl isocyanate. Alkyl isocyanate after hydrolysis we get, and this is the usual procedure that we have seen in the previous cases also. This is Smith reaction, where a carboxylic acid is first of all treated with a mineral acid and then with hydrozoic acid, and the end product is an amine, and the detailed mechanism is here. A carboxylic acid on treatment with a mineral acid, the OH getting protonated, generating an acylium ion. That acylium ion reacts with hydrozoic acid as shown in this mechanism, gives this product, and that after rearrangement becomes alkyl isocyanate. That reacts with water forming the carbamic acid, which is given in protonated form here, and that on heating we end with a primary amine. And these are some of the methods available for the preparation of amines, and the reactions of amines we will continue in the next module. Thank you.